Hello, my name is Ashwin Rao. I'm the founder of a startup and also an adjunct professor in applied math at Stanford University. Today, we're going to talk about where we have landed with AI and how we got here, and maybe a little bit about where we're at. So our LinkedIn feeds are full of posts like these, which are indicating that AI is magically solving everything now. So let's investigate and see if that is indeed the case. So here's an example where we ask a question: how can I start a three-way financial model in Excel? What data do I need? Gives you very precise instructions on what to do, including details on the data, how to build a model. This is pretty impressive. And closer to home, if you ask modern AI systems, write a Python script to write a record to an Aerospike database, this is really specific. You have to get the code right. It has to know about Aerospike. But look at the response. It is extremely impressive. It tells you what to install, the exact details of the code, and even things like, this should be the local host, and incredible amount of detail. This is really amazing. So is it really solving everything now? So let's investigate. The first thing I would say is that as far as speed of tasks is concerned, it's improved a lot. If you look at the first two examples that I showed you there of the financial model and of the Python script, you could have done that even before this recent spike through Gen AI. You would have searched on the internet, maybe gone to Stack Overflow. It might have taken you 30 minutes, 60 minutes, something like that to solve the problem. And now you can do it in like a few seconds, really. So that, I would say, is the biggest effect of where we have landed with AI. Now, where is it working really well? You look at software development. I can tell you as a programmer myself, I've had a 20% improvement in my speed of software development, and that's significant because I use Copilot. So when I'm programming, it's writing code along with me. We're collaborating and producing code that's faster. In marketing, I'm not in the field of marketing, but my colleagues in marketing tell me they're also having an enormous impact in how fast they're able to produce stuff. And also as an educator at Stanford and elsewhere, I am starting to use AI and finding enormous benefits. The speed is definitely up. Creative content generation, you've seen all these poems and music being generated by AI, art. It's all very impressive. But along with speed, you also want quality of results. And this is the part that's not clear to us. Sometimes we find that AI produces inconsistent or unreliable results if you leave it on its own. So what is really required to make AI work is you have to have AI systems work with a human. The human involvement is important. And this is where the chat of ChatGPT is key, that you iterate, you ask questions. If the response is not correct or you're not happy with it, you provide some feedback. The AI system will respond and adapt. And really, the idea is to collaborate with the human to solve the problem. So the way to use modern generative AI is you combine the best parts of the machine and the human. So Gen AI's strength, like I said, is the speed, but it also has enormous broad knowledge of all kinds of things, right? It knows everything that's out there on the internet. The human strength is orthogonal to this. Humans have enormous domain knowledge and a lot of judgment, nuanced judgment of what to do when you have to make good decisions. So if you combine these two things, that's when you start getting a lot of benefits. Now, what's not working? Here are some examples. At Stanford, I work on financial applications, and a lot of people ask, now, can AI predict the stock market? The answer is clearly no. And we'll try to understand why in a bit. Another example here is you have an injury. I had a back injury last year, and I can get a lot of information on the internet on generic advice. But for my specific situation, can I use AI to help me solve my back problem? And, even that is not quite working. I'm not saying it will not work. At some point it will work, but today this is not working. Something even simpler. I want AI to just figure out how I eat, how I order, learn from my patterns, and decide what groceries to order. This seems pretty straightforward. Well, there are challenges here as well. I don't think today's AI can solve this problem autonomously. I'm a parent to two teenagers. I'm pretty sure AI, as much as I think I'm doing a good job, I would like some help, but I doubt that AI can help me, be a better parent. And in our workspace, all of us are trying to make important management decisions, which are very complex. And again, this is not something AI can solve just yet. So we should all think about what are the features of these problems which makes it difficult for today's AI to penetrate. So for that, let us step back a little bit in time and try to understand how we got here. So there's a long history of AI, started with the 1950s, perhaps you could argue even before, where some of the seeds were set. There was a first AI winter in 1970 when, after a lot of initial hype about AI, things just died down. And then in 1980s, there was this revival of AI happening. After the first winter, you had this system called expert systems where humans came up with specific domain knowledge and provided huge databases of domain knowledge. That was the model of AI. And there was also a revival of neural networks. Remember, these neural networks that work today were actually built about 50, perhaps 60 years ago. But then in the 80s, there was a good revival of neural networks. But then late 80s, early 90s, there was a second AI winter because expert systems, which were hyped up so much, they didn't work out. And then the real progress started happening from mid-90s to 2010, when I would just say that Moore's law was the reason for the success, but compute power just kept growing so much that things that people were trying to solve previously that failed because of poor compute power suddenly started working. And so there was a lot of behind the scenes practical progress that happened over those years. And the modern world, which I would call the 2011 to present, is about big data and about deep neural networks. And I'll talk about shades of general AI, which is what we call AGI. So what is big data? Well, up to 2010, we had lots of compute power helping AI. And then along came large amounts of data collection, data engineering that combined with compute power and really propelled machine learning and made AI, all the AI dreams of the past really possible. The big game changer was really deep learning. So what's deep learning? Well, it's a neural network, but now with tons and tons of layers. So Jeff Hinton in 2012 built this neural network, which had many layers, many parameters. It's a large neural network. So what happened with is compute power, big data, and these very deep neural networks all came together to propel AI. And what we saw by the end of the previous decade is we were solving some very tough problems in text and images. And now in the last few years, we're starting to penetrate related problems as well. And of course, 6 months ago, ChatGPT was launched, and that has been a step change in terms of how much AI is solving problems and really has caught the imagination of the larger population. So let me demystify some of this jargon that is associated with AI. The first thing you'll hear about is like this narrow and general AI. Narrow AI means you build a system to solve a specific problem. So let's say you build something to play the game of chess, and that's all it can do. It cannot play other games, but you make it so good that, it is really valuable to you. That's narrow AI. General AI is this idea is that I build a system that can solve pretty much all problems, or at least a very wide range of problems. So there's a lot of focus on general AI. We call it AGI today. A lot of systems are built not to solve a narrow problem, but like broader. So ChatGPT could be argued as something that is headed in the direction of general AI, because it's not just meant to, solve a specific problem. Like, I want to classify images, or I want to be able to, write a math textbook. It can do a variety of things. I want to talk about this term Gen AI. Gen AI, the term has come as contrasted with discriminative AI. So discriminative AI is a problem where you have to classify things. So if I give you images of animals, millions of images of animals, discriminative AI would just classify them and say, these pictures are of dogs, these of cats, and these of horses. That's the idea of discriminative AI. Generative AI, on the other hand, would not be in the business of classification. It would generate images or generate text. So in this example, it would generate pictures of different types of animals, something that would look like a dog, or something that would look maybe like a hybrid of dog and cat. And that's the hallucination part of generative AI. It could actually generate images of animals which are not even real. And this is also important to understand that learning AI is a lot in vogue today. And there's also this other type of AI called planning AI. And I feel like the real success of AI in the future will come by combining these two. Planning is this idea that you build a model of your environment. You build a mathematical model and you search through your model. I just want to learn directly from data, go directly from data to the solution of the problem. And so today, machine learning is really the learning approach to AI. Now, this classification of the levels of AI, I feel, is very important. Assistive, augmented, autonomous. Let me illustrate this with an example of driving cars. So assistive is the most basic form. where you're driving a car. This is like, about 10 years ago when we didn't have autopilot and these self-driving features. But what we had was cruise control. So when you have basic assistance like cruise control that improves your productivity, we call that assistive AI. So remember, when you put it on cruise control, it is a machine that is doing a lot of control over your car. But the machine is not in control. You're in control and you're just getting assistance. The next level is augmented AI. This is your modern, Tesla car, where sometimes the machine is fully driving, sometimes you're driving. But really the idea is that the machine and the human come together, they collaborate to create better outcomes. The sum is greater than the parts. And the future is going to be autonomous AI, where you completely solve the problem. The machine completely solves the problem without any human help. So today we are at the stage of augmented AI. I would highly encourage all of you, when you start thinking about building AI systems, not to initially think about building autonomous AI, but think about constructing it in the direction of augmented AI. Now, a little bit of, again, some more terminology, types of machine learning. You've got supervised, unsupervised, and reinforcement learning, the three types of machine learning we do today. Supervised is the idea which is it's task-driven, it's trying to predict the next value. Unsupervised is given data, you try to identify clusters, and then we'll talk about reinforcement learning. Let me explain with some pictures. So the simplest form of supervised learning is regression. All of you know about it. Supervised learning is this idea that I have some data and I put labels on this data. This example of images of animals would be example of supervised learning. You have all these images of animals and you're asked to predict what is the name of the animal. The data that is provided for training has the images and the names. The names is what we would call labels. In the case of this regression problem, your X values of this data is your given data, and the labels are the Y values. So all these like blue dots, that's your data. They're all labeled. Remember, the height of those blue points is your label. A different example here on the left, I have supervised learning where I have two dimensions of X. So let's call the horizontal X1, the vertical as X2, and the label is really the color. Y is not a numerical value, but Y here is just blue or red. Okay, but X1, X2 is the given data. So I create these labels and it learns from this. So what it's going to say is like, I can see kind of the southwest is all red and the northeast is all blue. And it's going to try to draw this line, which is like classifying and saying, okay, this is kind of what I've learned, that everything below that line is going to be red, which is not going to be always right, but it's going to be right most of the time. And everything above is going to be blue. That's the model. So it's going to predict, given a new point, whether it's going to be red or blue. Unsupervised here on the right is a different situation. You've got these points, again, X1 and X2 data, but there is no label in this case. And I just asked this question that I'm going to create clusters of the data. So if you ask a human, can you create clusters? They're going to say, yeah, I see some stuff here on the southwest. That's one cluster, and then the northeast is a different cluster. Right? So this is what it would do, unsupervised. So you have to understand, one is taking advantage of the labels, the other doesn't have any labels, it just clusters. Now, reinforcement learning is the more like complex form of machine learning. This happens to be my area of research at Stanford. This system is a time-sequenced optimization system. So let's try to understand it. Here, you have the agent and the environment working in a time-sequenced loop. At every time step, the agent, which is the thing at the bottom, is going to look up the current state of the environment. In the case of a self-driving car, the state would be all the information it sees from the sensors of the car, the other cars, the streets, the weather conditions. State is an abstract concept. You can define it what you want to be depending on the nature of the problem you want to solve. Okay, so lots of problems can be modeled with this. So agent looks at the state, performs an action, and then interacts with this environment. Environment is also an abstract entity, depending on the nature of the problem. And in the case of a self-driving car, the action is going to be the steering wheel control and the acceleration braking. The environment provides a state, performs an action, receives a thing called reward, and this loop keeps repeating. So agent receives state and reward, and its job is to perform the most optimal action so you maximize your cumulative rewards from this point onwards. This is sort of a time-sequenced control system under uncertainty because states and actions are random. So like I said, you incrementally learn from data that is coming in, and you keep improving through trial and error. You perform an action. If you get a poor reward, you say, I'm going to de-emphasize this action. And if you get a good reward, you emphasize this action. That's where the word reinforcement comes from. The way RL really works in practice is that the environment the agent is interacting with is often not the real environment. You cannot train the self-driving car on the street, because if it performs all these trial and error actions, it will crash and burn. So you create a simulated environment. And simulated environment can then give you streaming real-time data so you can continuously learn, because you really now with simulated environment, you have infinite access to data. And so this is where I believe Aerospike has a lot to contribute in terms of building real-time data architectures to help machine learning systems like reinforcement learning. Now, there's a lot of problems where you can do RL. Talked about cars. The game of chess is one of the famous problems that was solved with RL. Some of my research is in managing investment portfolios, where the action is like rebalancing your portfolio. The reward is just making more money, right? I worked at Target on inventory replenishment, also RL, and then GPT turned into ChatGPT because of RL. So what were the game changers in where we have arrived at today? Well, I told you about deep neural networks with large number of parameters. That was a big game changer. Large data sets. I really believe that engineering systems had a lot more to do. I believe it was more impactful than the science. We won't talk about hyperparameters and embeddings. If you're curious, you can look it up. These were also very big parts of why we have succeeded. Transformers is the key in GPT. And of course, I have a bias. RL, I think, has been very influential. So when should you use AI and when should you not? Well, when you have a problem where you can tolerate errors in the solution, AI is in business. If you want high accuracy, then you'll have to be more careful. You'll have to involve some other techniques and systems and control beyond AI. Other reasons where the problem is suitable for AI is when AI can interact with skilled humans. And lastly, I would say problems where you have ample time to learn and tune. Okay, so this is my last slide. I'm going to dare to predict the future of AI. What's going to happen is AI systems are going to interact with each other and AI will keep getting better. This is a cycle that it will keep playing over time. I think software engineering is where you're going to see a huge improvement. People's productivity will go up enormously in software development. It's a big deal for the economy. You will see a lot of uptick in the area of information retrieval, my own world of education, advisory work, doctors, lawyers, things like that. And then when I talked about those 5 problems at the beginning that we have been struggling, the way to solve those problems is with very detailed data collection. And this is going to be a bit of a bottleneck. We have to have systems that collect data. I would say that there's going to be a lot of focus on privacy, bias, safety, ethics. Human skills will improve from AI. AI will become teacher, helping us do better at our jobs. And lastly, I would say, I was just telling your founder Aerospike's founder, that there will be a lot of legislative interventions in the world. With that, I will end my talk. Thank you and good luck with usage of AI in your business.